So when we mentioned the basics of inverse functions, there's one other thing that I really should have talked about, that because we're kind of flipping these things, the domain of a function becomes the range of its inverse, and the range of the original becomes the domain of the inverse. But anyway, for the sine function, we will end up getting something called sine inverse or arcsine, where there's one really important thing I want to mention here before I actually talk about what goes on with this, and that is, I don't like that notation, because that notation makes an implication here that sine inverse of x is the same as the function sine of x to the negative 1, which should be 1 over sine of x, which should be cosecant of x. This is not true. Not even remotely true, and that's the thing that'll get you in a lot of trouble when you get onto this stuff in calculus, making that sort of step. Don't do that, and I really don't like this notation because it implies that you should be able to. Really, that's why I prefer the arcsine notation instead. But anyway, when we're talking about getting an inverse, ignoring that we know where we're going to end up, we need something to be one-to-one. But thinking about the graph of sine, that's very clearly not one-to-one. The periodicity guarantees that it's going to cease to be one-to-one basically every copy of pi, if not even a little bit quicker than that in some cases. So if we want to get an inverse for this, we have to make a restriction. And technically speaking, we could make the restriction that we're going to work from here in any way that we want to. There isn't one specific way that we have to restrict sine to get inverse sine, but generally when we do this, we make our window from negative pi over 2 to pi over 2, including the endpoints. I don't know if there's a good argument for why we do that in particular, except that we like having negative 1 to 1 and going through the origin. That's what we use. The main thing here is when we get that value, when we get that much smaller window for our function, we can see that that's 1 to 1, albeit not very interesting. And if we want to get the inverse, we can get it graphically by flipping over the line y equals x, or we can talk about flipping all of our coordinates, because we're flipping domain and range, to get a picture something like this instead, where this is what our inverse sine function, the function sine inverse, looks like in terms of our construction, where it's important to know that for a function, the defining characteristic is that for every input, we get one output. That is, if I take some value and plug it in, it won't go to two separate places. Where if we wanted to let this thing keep going, we could see that it very much wouldn't happen when you flip it over and you end up with some weird vertical spring shape thing. So that's why we have to make that weird restriction, because otherwise we'd get in a whole lot of trouble with our construction. And for this, if you ever want to find values in terms of the inverse sine function, we essentially have 3 steps we can use, although it's a bit more than we really need. But what we can do is set theta equals sine inverse of x, remembering that sine inverse tells us something about a radius, tells us something about an angle in terms of a radius, where from there we rewrite that as sine of theta equals x for appropriately defined theta. And then you can either use a calculator or some well-known values of the sine function to get the desired value, where we have these basic ones here. Hopefully, by this point, looking at this material, you don't necessarily need this table to get every single point on here, but it is still good to have for practice, which is what we're going to do next.